Space is vast, an endless expanse that stretches beyond our wildest imaginations. It is filled with mysteries that boggle the mind, secrets that have puzzled humanity for centuries. Among these enigmas, black holes reign supreme, capturing the fascination of scientists and the public alike. These cosmic monsters, born from the death throes of massive stars, possess gravity so intense that nothing, not even light, can escape their grasp. They are the ultimate powerhouses of the universe. For decades, black holes were thought to be the ultimate cosmic vacuum cleaners, devouring everything in their path, leaving nothing behind. But then came a revolutionary idea, courtesy of a brilliant physicist named Stephen Hawking, who dared to challenge the conventional wisdom. In 1974, Hawking made a startling prediction that would change our understanding of black holes forever. He theorized that black holes aren't entirely black after all. Instead, they slowly emit a faint radiation, now known as Hawking radiation. This radiation, he proposed, arises from the bizarre quantum world, where particles pop in and out of existence near the black hole's event horizon, the point of no return. Imagine the event horizon as a turbulent sea of quantum foam, a place where the rules of physics as we know them break down. Pairs of virtual particles, one with positive energy and the other with negative energy, constantly flicker into being, only to annihilate each other in a flash. Normally, these particles annihilate each other in a flash, disappearing as quickly as they appeared. But at the edge of a black hole, something extraordinary can happen. Sometimes one particle falls into the black hole while its partner escapes into the vastness of space. The escaping particle carries away a tiny bit of the black hole's energy, reducing its mass ever so slightly. This process, though incredibly slow, has profound implications. The escaping particle carries away a tiny bit of the black hole's energy, reducing its mass ever so slightly. This slow leakage of energy, in the form of Hawking radiation, means that black holes are not eternal prisons. They slowly evaporate over eons, like a puddle of water drying in the sun. This slow leakage of energy, in the form of Hawking radiation, means that black holes are not eternal prisons. They slowly evaporate over eons, like a puddle of water drying in the sun. This groundbreaking idea has opened up new avenues of research and has deepened our understanding of the universe. Today, scientists continue to study Hawking's theories, exploring the intricate dance of particles and energy at the edge of black holes. The quest to understand these cosmic giants is far from over. As we peer deeper into the cosmos, we are reminded that the universe is a place of endless wonder, where even the darkest corners hold secrets waiting to be uncovered. And so, the story of black holes continues to unfold, revealing that they are not so black after all. Hawking's discovery sent shockwaves through the scientific community. It was a revelation that challenged the very foundations of our understanding of the universe. It was a groundbreaking moment, uniting two seemingly disparate realms of physics: Einstein's general relativity, which governs the universe on the grandest scales of stars and galaxies, and the mysterious, often counterintuitive world of quantum mechanics. Quantum mechanics describes the universe at the subatomic level, where particles behave in ways that defy classical intuition. It's a realm where particles can exist in multiple states at once, and where the act of observation can alter the outcome. Before Hawking, these two pillars of modern physics stood apart, like two languages struggling to communicate. General relativity and quantum mechanics were like oil and water, each powerful in its own domain but seemingly incompatible. General relativity described the smooth, continuous fabric of space-time warped by massive objects, painting a picture of a universe where gravity is the sculptor of the cosmos. Meanwhile, quantum mechanics spoke of a world of discrete particles and probabilistic interactions, where uncertainty and probability reign supreme. It's a universe where particles can pop in and out of existence, and where the very fabric of reality seems to shimmer with potential. Hawking's insight was to bridge this gap, showing that the intense gravity of a black hole could interact with the quantum vacuum, giving rise to the phenomenon of Hawking radiation. This was a monumental step, suggesting that black holes are not entirely black, but emit radiation, slowly losing mass over time. Imagine Einstein and Niels Bohr, the fathers of relativity and quantum mechanics, respectively, meeting for a chat in a cozy Viennese cafe. They sit at a small table, the air thick with the aroma of freshly brewed coffee, each lost in thought. They sip their coffee, deep in thought, each pondering the mysteries of the universe. Einstein, with his shock of white hair and piercing gaze, speaks of curved spacetime and the dance of celestial objects, his voice filled with the wonder of the cosmos. Einstein, with his shock of white hair and piercing gaze, speaks of curved spacetime and the dance of celestial objects. He describes a universe where massive bodies like stars and planets bend the fabric of spacetime, creating the force we perceive as gravity. Bohr, with his gentle demeanor and contemplative eyes, counters with tales of quantum jumps and the uncertainty principle. He speaks of a world where particles can be in multiple places at once, and where the act of measurement can change the outcome. Now picture Stephen Hawking entering the cafe, a twinkle in his eye and a mischievous grin on his face. He joins the conversation, bringing with him a revolutionary idea that would forever change our understanding of the universe. He sits down with the two titans of physics and unveils his theory of Hawking radiation, a theory that suggests black holes are not the eternal prisons they were once thought to be, but rather, they slowly evaporate over time, releasing energy back into the universe. This theory weaves together the threads of gravity and quantum mechanics into a tapestry of cosmic wonder. It suggests a universe where the very large and the very small are interconnected in ways we are only beginning to understand. A universe where the dance of particles and the warping of spacetime are part of the same grand ballet. The idea that black holes could evaporate challenged the prevailing dogma. It implied that these cosmic behemoths, thought to be immortal, had a finite lifespan. But there was a catch. The rate of evaporation is excruciatingly slow, especially for stellar mass black holes. A black hole with the mass of our sun would take an unimaginable amount of time to evaporate, far longer than the current age of the universe. In fact, it would take a Google years, a number so large that it makes a billion trillion years seem like a fleeting moment. However, smaller black holes, hypothetical remnants of the Big Bang called primordial black holes, could evaporate much faster, potentially releasing a burst of energy detectable from Earth. Think of a black hole as a giant cosmic pressure cooker. The more massive the black hole, the higher the pressure inside, and just like a pressure cooker, the hotter it gets, the faster it cooks. Small black holes with their intense pressure would cook much faster, eventually evaporating in a spectacular burst of Hawking radiation. So, while we might not be around to witness the final evaporation of a stellar mass black hole, the search for these dying embers of the early universe continues. Hawking radiation, it turns out, might not be exclusive to black holes. This groundbreaking idea challenges our traditional understanding of where and how this radiation can occur. Recent studies suggest that this bizarre phenomenon could be a universal property of gravity, applicable to any object with mass, including stars and planets. This means that the very fabric of our universe might be teeming with faint whispers of Hawking radiation emanating from all sorts of celestial bodies. The key is the concept of a gravitational horizon. This horizon is not just a feature of black holes, but a fundamental aspect of any massive object. Just as a black hole has an event horizon from which nothing can escape, any massive object has a gravitational horizon, albeit much farther out. This horizon is the boundary where the gravitational pull of the object becomes significant enough to affect the behavior of light and other particles. This horizon represents the distance at which the object's gravitational pull becomes strong enough to trap light. It's a fascinating concept that extends the reach of gravitational influence far beyond what we can see. While this horizon is far less extreme than that of a black hole, it still creates a region where Hawking radiation could theoretically be produced. This opens up a whole new realm of possibilities for where we might find this elusive radiation. Imagine standing on the surface of the sun if you could withstand the heat. The sun, with its immense mass, has its own gravitational horizon. Now, picture a tiny photon, a particle of light, trying to escape the sun's gravitational clutches. This photon is in a constant battle against the sun's gravity. As the photon struggles to climb out of the sun's gravitational well, it loses energy, its journey becoming more arduous with every passing moment. Its wavelength stretches and becomes redshifted, a clear sign of the energy it is losing in its struggle to break free. At a certain distance, the photon loses so much energy that it can no longer escape, trapped by the sun's gravity. This point marks the sun's gravitational horizon. This is the sun's gravitational horizon, and according to some theories, it could be a source of Hawking radiation, albeit incredibly faint. This faint radiation is a testament to the subtle yet profound effects of gravity. While the amount of Hawking radiation from a star or planet would be minuscule, far too faint to detect with current technology, its existence could have profound implications for our understanding of gravity and the universe. It suggests that Hawking radiation is not just a feature of black holes but a universal phenomenon. This revelation could lead to new insights into the nature of gravity, the behavior of light, and the fundamental workings of the cosmos. It opens up new avenues for research and challenges us to rethink our understanding of the universe. As we continue to explore these ideas, we may find that the universe is even more interconnected and dynamic than we ever imagined. The study of Hawking radiation from stars and planets is just the beginning of a new chapter in our quest to understand the cosmos.